also asked questions on 2330, which is the synthesis problem, so you can see the reactions in context. The first of these reactions takes benzene and reacts it with an acyl group in the presence of aluminum trichloride. Because of this, it's a straightforward acylation, and so we should end up installing the acyl group on any of the positions, which are all identical. We have 1, 2, 3, 4 carbons, 1, 2, 3, 4, and it's shaped like this. The next reaction is a Clemmensen reduction, which you can find in your chapter 19 notes. The Clemmensen reduction takes the carbonyl and reduces it down to an alkane. This is one of the only ways that we can get an alkane like this that has a primary connection to the ring without rearrangements. If we tried to alkylate directly, we would not be able to do this. Reacting this with nitric acid in the presence of sulfuric acid allows us to nitrate. Now the positions that we can nitrate at are going to be determined by this group. Because this is an alkyl group, it's ortho-para-directing, ortho or para, and because it's large, it's going to be mostly para. So that's what I'm going to choose to draw as my major product. So I'll have this ring, and now I have the nitro group at the para position, NO2. This HCl and iron is a reducing condition. So we're able to reduce specifically this NO2 group to an NH2 group. Technically it would be NH3 until we treat it in any sort of base, NH3 positive, but we generally just write this as NH2. NaNO2, sodium nitrite, notice this is different than nitrate, is our standard Sandmeyer conditions to install the diazonium salt. So to remind you what that looks like, we have on the nitrogen now what essentially is a nitrogen gas type group, and that's balanced by whatever counter ion is present here, in this case Cl-. That's still going to be across from the same alkyl group. This group is really capable of substituting, sorry, I realize there's a little bit of glare there, so I'm pushing this up a little bit, substituting in the presence of copper salts. So we can swap out this group for a lot of other groups if we have a copper catalyst. We're able to do that then and substitute in a cyanide instead of this group. So once we have a cyanide here, now we can go through a Grignard reaction. The Grignard reaction is going to have nucleophilic carbon attacking onto the most positively charged carbon on this ring. Because we don't end up forming the carbonyl until we have H3O+, we end up with a single addition, and we end up having the carbonyl at that location. Sorry, I'm blocking this a little bit. So we end up keeping the same alkyl group over here, and then over on this side, we end up with a carbonyl, and then we added on the 2 carbons here. 1, 2 carbons, 1, 2 new carbons. What initially forms as an imine through the addition of this reaction ends up becoming the carbonyl, the ketone, because of the acid workup. And of course, it's still aromatic, so we still need those in that present part. The last condition is sodium borohydride, which is a reductant. It's not the same as this Clemmensen reduction. It will only reduce this carbonyl to the alcohol. And so we end up with aromatic with the same side chain that we've had for most of this. And over here, we now have an alcohol on that benzyl position, and we have still the aromatic. So our final product is this.